Alright, so let's load up some data to do the Munk model fitting. We'll write a script, and the data for the World Ocean Atlas, remember, comes in the netcdf, so we need that package, and we're going to make some plots to see what the data looks like. So the first line loads the package, the second line sets the current directory where the file is, and there's a typo, there should be 2 underscores before the file and 2 after. There we go. And now I've typed in the file names, just like before, for the World Ocean Atlas data in my directory. First for the temperature, and then for the salinity. Even though we're just going to fit the temperature profile, we need the salinity so we can compute the conservative temperature, because that's the one that has no sources or sinks. The long from the World Ocean Atlas and the depth, and I convert all the data to float 64 as before. It makes it easier to use the Gibbs seawater functions. Alright, read the data, and then I'm going to filter out all the missing values that have large numbers and replace them with nans. And first thing we'll do is we'll make a plot of the surface temperature, the SST, so we can orient ourselves where we want to set our region to fit Munk's model. Alright, so there's the map. We're going to pick a region in the North Pacific. In order to pick the region to select the data, we're going to make these 3D arrays the same size as T annual and salt annual, and we're going to put the latitude, longitude, and depth in these variables. So I'm going to cycle over each of the grid points and assign a variable latitude into those 3D arrays. So Y is latitude, X is longitude, and Z is depth. Alright, so we run that code and check the size of these arrays, make sure they're all the same size as the temperature field. Alright, so now we're computing the absolute salinity using the Gibbs seawater equation, thermodynamic equation. And we're doing this for every point in the World Ocean Atlas. So we need to load the package Gibbs seawater first, and now it should run. Alright, correct the name. And now same thing for the conservative temperature. Right, remember the absolute salinity is an input to the conservative temperature equation. Alright, now we want to load in the radiocarbon data, and I get that from the GLODAP v2 database, and that database, you can read the data in a MATLAB file, and I thought that was the easiest way to get the data. So the one I'm going to use is the merged master file, and it's a .mat, and that's why I have the package, the mat package. So it's a Julie package that allows me to read MATLAB binary data sets. Alright, so now we're going to read in the GLODAP v2 data set. First we open the file, and then we read in, first I'll read in the depth, and so that mat open should be read. There's a mistake there. There we go, that should be, yeah, read. And then Y is going to be the latitude, X is the longitude, and C14 is the delta 14C values. And I'm going to use lowercase xyz for the radiocarbon data set, and uppercase xyz for the World Ocean Atlas data set. Okay, so now we want to pick a box in which we're going to do our vertical fitting. And there's a kind of trade-off going on here. The bigger the box is, the more data we have, but then we're going to include a lot of horizontal variability in our estimate. So we don't want to do that. So it's we want to have a data set that's big, yet not too big. Did you notice I changed the depth to be minus negative Z, right? So Z is positive upwards. All right, so the box I've decided to pick is going to be between 20 north and 45 north, so in the subtropical mid-latitudes. And the east-west boundary, the western boundary is going to be at 160 east, and the eastern boundary is going to be at 120 west. The top of the box will be at 1,000 meters depth, and the bottom of the box is going to be at negative, or at 4,000 meters depth. All right, so now I'm doing all these logical cases here, making sure that the X and the Y values are within the bounding box. And the little dot ampersand, that means and, so both conditions have to be true. The dot with the bar, that's an or statement, so I use that for the longitude because you have to be either bigger than the western side of the box or smaller than the eastern side of the box. And then I'm going to see how many data points I have. It's 1,485, and I'm putting a print statement just to write it out neatly. Right, so a total of 1,485 radiocarbon data points were found within that bounding box. And we're going to make a scatter plot of it, see what it looks like. So the radiocarbon data is not gridded data set, so the vertical position, it depends at the depth at which they collected the water bottles to make the radiocarbon measurements. So it hasn't been gridded. All right, so now let's get the data within the box from the conservative temperature. I'm going to use the same conditioning to find all the indices in the World Ocean Atlas that fall within the bounding box. And now I'm going to use the uppercase letters X, Y, Z instead of the lowercase one. So I'm just going to copy the statement I used for the radiocarbon and replace the lowercase x's, y's, and z's with the uppercase ones. And I need to have these colons because X, Y, Z are 3D arrays, and I want to make them to one single long list. And the colon does that. Let's make these code neat. There we go. Make sure all my parentheses are buttoned up. There we go. Success. And now let's check. OC is positive, so I have to add a negative because I want Z to be positive upward and negative into the ocean. 0 at the sea surface. And now I'm going to print how many data points I have in the box for conservative temperature. And print those out. So I have 77,000, a little bit more than 77,000 temperature points, and 4,000, around 1,500 points for radiocarbon. All right, let's make a plot of the temperature as a function of depth. And here you can see that there's gridded data, right? All the depth levels are the same. And you also see that as you go up into the water column, there's a lot more spatial variance in temperature than there is for radiocarbon. Okay, that was a good time to pause the video here and take a breather. All right, hopefully you're back. Let's look at modeling the Munk model. So I'm creating a function AD, which is going to solve the 1D advection diffusion equation with parameters delta and lambda, as I explained in the lecture. So this is the equation we're solving. The divergence of the flux is equal to the sinks, and that, if we replace it in terms of delta and lambda, becomes the following equation. So the stuff in green here, between the triple quotes, these are all comments. So that's not actual Julia code. That's just comments for me. We try an exponential solution where r is to be determined, and we get the characteristic equation. R squared minus r delta is equal to lambda. We solve that using the quadratic equation. There's two roots, and here's the solution in terms of the quadratic function. The quadratic formula, sorry. Should be a plus, there we go. And I divide by 2. Okay. And I want to make a note here that in this code, if I want to do temperature, where there's no sources in sink, I should set lambda to 0. So delta is the only parameter, and the equations are going to be correct with lambda equal to 0 for conservative temperature. All right, now this is actual Julia code. Finding out the true roots of the quadratic equation as a function of delta and lambda. And now the boundary conditions, so BC1 and BC2 are going to be pairs of values. The first being the depth at which we apply the boundary condition, and the second one, the value of the tracer at that depth. And there's two boundary conditions, one at the top and one at the bottom. And now we're going to use those boundary conditions to determine the constants of integration. And I called it A, so it's going to be an A1 and an A2. And what the function AD returns is going to be another function, and the function will be of Z, and it returns a solution, right? So it's going to take in Z and return A times e to the R1Z plus, or A1 times e to the R1Z plus A2 e to the R2Z. All right, let's try it out on the temperature. And the input parameters are delta is 1 times 10 to the minus 3. And for lambda, I put in 1 times 10 to the minus 10. It should be 0 if I'm doing temperature. And the boundary conditions at 1,000 meters and 4,000 meters are 4 degrees Celsius at the top and 1.2 degrees Celsius at the bottom. And here's a scatter plot. It's in red, you can't really see it. So I'm going to replot the data, and this time I'm going to change the stroke around the little symbols so that it doesn't show up. And also I'm going to make the symbols a little bit fainter by using an alpha value, which makes them a little bit transparent. So I'm replotting the data. The marker stroke width, I'm going to set it to 0, so no marker around the little symbols. The marker alpha will be 0.1, so they'll be nearly transparent. There we go. And now I'm going to replot on top of that the model. And you can see it's a little bit below the data. It's a pretty good guess at what the value of delta should be. If I increase the delta, that makes it more diffusive. Or, sorry, decrease delta makes it more diffusive. And then it's mixed more uniformly. If I make delta bigger, that's more advection. And now you can see that the water fills in, the water column fills in with the value from the bottom, right? So upwelling fills up the whole water column, as I explained before. All right, now let's make a similar plot for the radiocarbon data. Here's the data. And okay, make it a little bit less faint because there's less data. And here's trying to fit the radiocarbon. So let me try again. Too much decay. Try a little bit less decay, better. Still, oh, made it worse this time. I had more decay. I went the wrong direction. 10 to the minus 8 less. Overshoot. 7. Undershoot. 5. I'm going to make it even worse. I got to go the other direction. 10 to the minus 8. There we go. Okay, that's better. So you can see that you can try to play around with these parameters till you get a good fit. It's better to use an automatic optimization method. So what I'm going to do is I'm going to make a function, call it g, which is going to be return how well I fit the data. So kind of a goodness of fit or measure of misfit. And that function is going to take in some parameters, p. It's a vector of parameters, and the first one, p1, will be the logarithm of delta. So I know delta is positive, so I'm going to optimize the log of delta. Then it doesn't have to be positive. The log doesn't. And lambda will be the log of lambda will be the second parameter. And then there'll be 6 parameters in total, delta and lambda, plus the 2 boundary conditions for temperature and the 2 boundary conditions for radiocarbon. All right, now I'm going to solve for the temperature, the conservative temperature. So that T will become a theta, yes. And I should have lambda to 0. I'll catch that mistake in a little bit and correct it. Now I'm going to solve the solution, and I'm going to evaluate it at the depths of the conservative temperature, where in the World Ocean Atlas. And I'm going to take the difference of the model minus the data and square it and sum it. And you notice I divided through by the number of data points. That's to give about equal weight to the temperature and radiocarbon data in the fitting, because there's a lot more temperature data. So the P3 and P4 are the boundary conditions for temperature. P5 and P6 are going to be the boundary conditions for radiocarbon. And you notice I'm going to have to change the delta here to 0, the lambda to 0, I mean, right? Because temperature doesn't have any radioactive decay. Now I'm solving for radiocarbon. I need both delta and lambda and their boundary conditions. And then I'm going to write the second objective, which is to minimize the misfit between the delta 14C of radiocarbon from the model and the observed radiocarbon. Right. IK2 are the indices for conservative temperature, and IK1 are the indices for the radiocarbon. Right, IK1 and IK2 pick out the points that are within the bounding box. All right, so then I transform the model output into a delta 14C by subtracting 1 and multiplying by 1,000, subtract the data, and this time I'm going to divide by the length of IK1, and I multiply by 100 because the delta 14C are of order negative 100, the magnitude is 100, and make them the same units, dimensionless. So it's kind of a crude way. There should be a better way to scale those using the standard deviation of the data, but this is good enough for a first try. Okay, now we're ready to optimize, so I have to set an initial iterate for the parameters. Remember, I'm optimizing the log of delta and the log of lambda. and I have to re-exponentiate to get the actual delta and lambda values after. And then I need the initial guesses at the upper and lower boundary conditions for temperature, upper and lower boundary conditions for the radiocarbon. All right, and now I use the optimize Julia function, and of course I didn't see, I had an error. I put BC1 and BC2 both at 1,000 meters, so I was applying inconsistent boundary condition, and LabPack told me that by returning an error, so it's fixed now. All right, so success, we had a successful optimization. P hat is the optimal value, and then we compute delta by exponentiating P hat 1, lambda by exponentiating P hat 2. From lambda and delta, we can compute K and W. So we need the radiocarbon loss frequency rate, lambda 14. Then we compute K, and from K, we compute W by dividing by delta. All right, so let's print out the optimal values using a print statement, a formatted print. So the best fit W in meters per second is W, and then the best fit diffusivity in meters squared per second. Actually, it's a small number, so I'll multiply by 10 to the 4 meters squared per second. Sorry, 10 to the minus 4 meters squared per second. Right, so I multiply, and then in the units, they're 10 to the minus 4 meters squared per second. Multiply by 10 to the 4. It'll make it a bigger number. All right, so we have W best fit is about 7 centimeters per second, and the best fit diffusivity is about 10 to the minus 4 meters squared per second. So it's similar to what Munk got in his original Abyssal Recipes paper. All right, let's replot the data with using the best fit parameters. So use the delta, use the delta and lambda for radiocarbon, delta and 0, and then put the best fit upper and lower boundary conditions for the potential temperature, best fit upper and lower boundary conditions for the radiocarbon, five and 6. All right, now let's make the plots. So there's a temperature, and there's the fit, and it goes through the data. So it's a pretty good model. And I'll put some labels. So the x-axis is conservative temperature in degrees Kelvin. I guess they're not degrees Kelvin, right? These are degrees Celsius, so that's a mistake. And then the delta 14C in per mil. And the y label is the depth. And let's plot those results. And there we go. So a decent fit. All right, that's it. Thanks for watching.